throttleTime operator lets an emitted value from the source pass, then activates a timer, ignoring all values until the duration you specify has passed. If we add time markers to the diagram, we can see the first item is emitted, then values within the timer window are ignored. This behavior is then repeated for the next emitted value from the source. Some use cases for throttleTime include recognizing certain user events such as double clicks, or limiting updates from more spammy event streams such as scroll events. Let's start with the first click example from the previous lesson to understand how throttleTime compares to debounce time. If you recall, we had a click stream with the document as a target. We were then using debounce time to only emit the last click event after 1 second had passed between clicks. So when we click on the document, nothing will happen until we pause for a second, then the click event is emitted. Let's switch out debounce time with throttleTime to see how this compares. We can go ahead and add the throttleTime operator to the operator's import. And we'll just swap out the debounce time operator with throttleTime within the pipe method for our click stream. Let's actually set this to a longer duration, let's say 3 seconds, so we can better see the behavior. When we save, what we will see is the first click will be immediately emitted, then all values are ignored if we click again for the next 3 seconds. Once the silence window is passed, the next click will be emitted. So throttleTime can be extremely useful in scenarios where we have a spammy event and we really only need to do work after longer periods of time have passed. One such example is a scroll progress bar that we built in an earlier lab. As a refresher, we created a stream of scroll events which we then transformed into a stream representing the percent the user has scrolled through the page by using the map operator and our calculate scroll percent helper function. We then subscribed and updated the progress bar element with on each emission. When we scroll down the page, the progress bar at the top is filled in. Let's see how we can update this example and use throttleTime to limit the number of calculations that are made while scrolling through the page. Let's actually start by importing tap so we can log every time a scroll event is currently being emitted. Next, let's add tap to the pipe method under our map operator and log each emitted value to the console. When we save, we can see just how often this is being run as the user scrolls through the page. While we aren't seeing any slowdown in this example, if this were a more expensive operation, we could run into issues with it being called too often. Let's see how throttleTime can help us out here. We can go ahead and add it to our operator imports. Now, before map, let's add the throttleTime operator. This will slow down the values being emitted to map to only 1 per the specified duration. So we can more clearly see the change this makes, let's set it to 200 milliseconds for now. When we save, we can see the scroll updates being emitted are significantly less due to the throttleTime operator. In reality, we probably want this somewhere between 20 and 30 milliseconds, so the scroll progress bar doesn't get jumpy. But even at this reduced duration, it will cause our calculate scroll percent function to be called significantly less. The last thing I want to bring up is the default behavior for throttle, which is emitting at the beginning of the silence window, might not be ideal for all scenarios. For instance, in this scroll example, it's possible that we could have made quite a bit of progress while in the silence window and stopped scrolling before the window was complete. In this case, our progress bar would not accurately reflect our current scroll position until we start scrolling again. To accommodate these scenarios, throttleTime accepts a configuration argument which allows you to set when the values should be emitted. To see this, we first need to import the async scheduler to provide as a second argument. You can ignore the details of this for now, as schedulers are a topic for our advanced course, and we are just supplying the default scheduler for this operator. We can supply this as a second argument to throttleTime, with the third argument being the config options. throttleTime accepts a config object with leading and trailing properties, which correspond with when the values should be emitted. The default behavior which we have seen thus far is to emit on the leading edge of the silence window, and then ignore all values until the window has passed. In the case of our scroll, we actually want the value to be emitted on the trailing edge, which means the last value at the end of the silence window. This will give us the latest scroll position after each silence duration has passed. If we go back to our diagram, we can quickly see how this shifts the emitted values from the leading edge to the trailing edge of the window, with the values 2 and 5 now being emitted, rather than 1 and 3. When we return to our example and save, we can see our scroll progress bar with throttleTime appears identical to our initial iteration, while now only calculating the current percent at most once every 30 milliseconds. To recap, by default, throttle time ignores values for a duration you specify after an emitted value. If you need the last emitted value at the closing edge of the timer, you can pass in a configuration setting for the leading and trailing properties. Now, if we put throttle and debounce side by side, throttle ignores values during a window after an emission, where debounce emits the latest value from the source after the specified time has passed between emissions from the source observable.